So let me share my screen to get us into this. Here we are. And I'm gonna put this on display now. Here we are. So the talk or the presentation is going to be on Los Erales Sintercone, which is one of the little sintercones in the south of Tenerife. And if you fly into Tenerife, you're going to see this alignment of sintercones that we have here in the first slide. And they are kind of part of the southern rift zone. And here we believe that we can document some changing eruption styles recorded in the sintercone. Now, this goes back to work by one of my students, Hilary Clark, and of course, Juan Carlos Cracedo was involved, and myself. And let me kind of go in there here. So we have these basaltic vent alignments. They're frequent in the Canaries, and most, actually all historical eruptions are in some form aligned with some fissures, some sort of lineaments, and they're part of rift zones, if you will. We see this on Tenerife, Gran Canaria, El Hierro, La Palma. Gran Canaria doesn't have any historical eruptions, but we see the rift alignments there as well. Vents are often associated with these rift zones, and usually they erupt in Strombolian style, but not exclusively. This is the most common style in the Canaries, but there can also be phreatomagmatic phenomena. And this is also something we have seen during the 2021 eruption on La Palma. There was phreatic or phreatomagmatic intervals during the eruption. So this is a bit odd because you wouldn't quite think that high up on the islands there's a lot of water available, while close to the coast there's plenty of water. So this is something we like to look at a little more, or this was at least our motivation at the time. So here we might have very localized explosive activity because of added water to the system's phreatomagmatic eruptions, and they are a little different. They're a little bit more hazardous than regular Strombolian eruptions. So we're going to go to the Canaries. We're zooming in. We are off the African, Northwest African coast. And here's Tenerife in the center of the archipelago, of the Canary archipelago. This is Tenerife Island, and here's the three rift zones. And we're going to go to the southern rift zone now, which is the weakest of the three. So this is this part here. And there's no historical eruptions on this part here. So the eruptions of Los Erales Sintercone, they are prehistoric. The historical eruptions are, however, along the northwest and northeast rift zone. So there is a possibility that future eruptions will again be along those rift zones. Now, these rift zones are also present in some of the old shields, and of course they're also present on the other islands, and they're also present in Hawaii. It's a typical feature of ocean islands, and it requires a little bit of thinking. The eruptions occur mainly along those rift zones. In fact, the rift zones, which are defined by vent alignments at the surface, they're well developed in the Canaries, and actually less so on Hawaii. But here we see them very clearly on the right-hand diagram here, the Cumbre Vieja, and here Tenerife, and here El Hierro. The Cumbre Vieja has a bit of a spread here as well, so this could become a triple-armed rift zone in the future as well. So, and as I said, the old shields had their own rift zone systems, meaning that there were their own volcanoes. So rift zones often develop once the volcanoes have reached a certain height, and I believe these rift zones are due to internal volcanotectonic phenomena. Now, but we want to go to the southern rift zone down here, and this is what we're after. So here we see the northeast rift zone. This is this part here, viewed from Teide volcano with the Naga, the old shield down in the clouds here. And here's a Google image showing this ridge, this dorsales, as the local people call it, the Cumbre Dorsal. And the rift zones at the below the surface is made of dikes where you have a bit of erosion or landslides. You can look into the rift zones, and there's dikes. And as I said, sintercones at the surface of this. So in the southern part of the island, we have this less strongly developed rift zone, but there's still sintercone alignments, and the sintercone alignment I've shown earlier is this one here. I put into this red box, And this is the Bandas del Sur, which is part of the depositional area of the Las Cañadas volcano. And this connects to the Las Cañadas volcano that was present 200,000 years ago and before, and then it terminated due to the Igot landslide. So, but during that period, there was a lot of ignimbrite eruptions and also sinter cone eruptions. And here we have several of those basaltic sinter cones aligned here. So they're not historical, they're prehistorical, I must stress that. That doesn't prevent us to learn from them. So here we have a map from Brian et al. 98, and he mapped several alignments here. These are clearly linked to fractures in the volcano, and they could well be representing some of these triple-armed things, but there's probably different fractures with different dominance on the fractures. So this is the fracture system we're looking at right now. This is where we have several of the volcanoes we are interested in, including Los Erales. So this is the one, as I said, and here we go. This is our alignment. North is up there, theta is up there in the clouds, and this is the sinter cone alignment. And the airport, the southern airport, Reina Sofia, is just to the right here. So now Los Erales, being one of the sinter cones in that alignment, well, it's been quarried, so we can look inside, and it sits next to a barranco, and there was a bit of a collapse there as well. So you can actually look inside, which makes it so special. This is very useful. And there has been lava flows emanating from the sinter cone, very much like La Palma in 2021. And what we see here is there's a rose, as people call it. There is a radial pattern of columnar jointed basalt, and this is an old lava tube or channel, a lava tunnel that was filled, and where the cooling was perpendicular to the cooling surface, and therefore then you get these radial patterns of columns. So, but what we're really interested in is the stratigraphy here. And as you see very clearly, there's a bit of reddish dark material up here. This is dark gray here, but in here, it gets all brown. And this brown color in the Canaries is rather typical for palagonite. Palagonite is a resin type, a glassy resin that forms from hydrated basalt. It's a decay product, it's metastable, and this gives this brownish, rather kind of earthy color. And this immediately tells us something is different here in the lower part of this stratigraphy than in the upper. Also, we see already here, there's big blocks in there. So something is a little odd. And here's Kevin, who was one of the mapping students at the time, and he's going over the little valley here. Here we see columnar jointed basalts, but this is the section, and Kevin is a good scale here. So here we see the dark areas, and here we have this brownish palagonite-rich areas, and this is the whole sinter cone in all its magnificence. So if we look through there, if we take a log through there, our initial hypothesis was that this lower part is hydrovolcanic because of the palagonite. There was a lot of water involved that allows to make palagonite. And then we have this grayish, dark grayish area, which we label as transitional. And then we have a classic strombolian capping sequence here. So it looks very much that the lower part was actually involving some water. It was hydrovolcanic or phreatomagmatic. And there, then we had a transition that was kind of more mixed, and then eventually we had a regular strombolian activity. If that's correct, then there was a change in eruption activity, and this is very useful to understand because as we've seen in La Palma, there can be changes of the eruption activity, and they can be quite rapid. So this is something we're not really have a full grasp of. So this is very useful to understand these changes. So again, here I'm showing the same thing, and it's very obvious here. Here we have the typical kind of sintery scoriaceous deposit. Here's this gray but laminated intermediate transitional area, and here we have the palagonoid-rich, finely laminated phreatomagmatic layers. So we can color code them here, and we should just call them here Unit 1, Unit 2, and Unit 3. And here is some rocks from Unit 1 to 3, and you can see the difference here. So this is Unit 1 on the right and Unit 3 on the left. So this is the phreatomagmatic rocks, this is the transitional ones, and this is the scoriaceous rocks. Now, we went to look at the particles, the pyroclastic particles, under the electron microscope, which allows us to zoom in a lot. And this is beautiful kind of material here. So here, from Unit 1, which we speculated was phreatomagmatic, we actually see very blocky shards, very blocky basaltic fragments. And this is quite typical for phreatomagmatic eruptions. They're not having had the chance to vesiculate in the same way, and they fragmented earlier because of the higher explosive energy, and therefore they are more blocky. And these moss-like particles have been described by Heiken and Wollitz already in the 1980s. And here's one of these moss-like particles, and here's a close-up of this. And these are very, very intriguing. And I'm gonna go to here, a real close-up here. So here we have one of these moss-like particles, typical for phreatomagmatic activity. Here's a few more. We have a few kind of bubbly shards here as well. And what we also see is we see some zeolites grown in some of the vesicles. And zeolites are usually happening to form at a few hundred degrees, and they are kind of an alteration product, and they require water to be present. So this is also an indication that this lower part could have been more water rich than the upper parts of the sequence at Los Erales. Now, the transition unit here, Unit 2, there we can see the shards are getting more bubbly, they're getting more spindle shaped, they're a little different, they're not as blocky anymore, so the eruption energy was not quite as high. And there we see elongated vesicles, and this means they were more fluidal, they were more strung out, and they were deformed during transport here. And this, of course, is very useful. So here's one of these areas that formed around one of the bubble walls, and this means there was less fragmentation if you see features that are still intact there. So, and I should also point out, I think, let's see, I should also point out, there's actually a little fossil here. So this was a diatom, and this implies that there was water present because diatoms live in water. In fresh water as well as in salt water, it doesn't tell us what type of water, but it means water was present. So this is very good. We have little fossils in there. So, and here the water is still present, and here I'm saying it fossil diatoms. So here we have one, and it's unclear, however, whether it was sea or fresh water. We had the botany department at Trinity College check at the time because Hillary was a student at Trinity College. But they couldn't give us a clear answer whether this was a fresh or a saltwater species because it was just not fresh enough. It clearly had gone through the eruption, was the point that was made to us. There's also a few nice minerals we see there, and they're not very fragmented. So the eruption energy seems to be lower than in the lower part of the unit here. So here we have nice magnetites, for example, and here probably blocky pyroxenes. So overall, there is some change. And here we have a zoom into this diatom. And here you see it's got a few particles attached to it. So this was clearly alive or was present during the eruption. It's not something that just crept in later on, which would also be difficult because they live in water. So you would have to flop the area or so if to get them in. And then you would expect them to be present rather universally, which is not the case. So little fossils in pyroclastic deposits, and then finally we move up to the Strombolian area, and there we see beautiful bubbles in the shards, in the basaltic pyroclast, in the tephra shards, and they're vitric, they're glassy, that means, and they're often kind of spherical, the bubbles, meaning that the bubbles were growing in a liquid state. They were not deformed, they were not forming while flying through the air. They were mainly forming when the material was still liquid and had already been deposited or was transported in a not very energetic way. So reduced pressure in the system, allowing for these more uniform bubbles. And we don't see any zeolites, we don't see any diatoms, we don't see palagonite either. So this is much more Strombolian, very typical for a Strombolian eruption rather than a water-rich eruption. So here we also see these kind of bubble areas that then allowed fragmentation of the tephra-clasts. What we also see is little droplets and beautiful little droplets and also beautiful crystals here. This is crystal shapes. Here's elongate prismatic ones. Here's more cube-shaped ones. And we have these gorgeous little droplets of magma of basaltic material. And well, that happens. They are typical for Strombolian activity. And there is almost no secondary alteration or overgrowth. Clearly, there was virtually no water involved to the best of our knowledge here, as opposed to the lower parts of the sequence where we see various indications for water to have been present. Now here, just because I like them so much, here's one of these droplets zoomed in, and this is of course microscopic in reality, but here we see one of these vitric glassy droplets here from the Strombolian deposits. Now, a few thin section observations. This was also done with the electron microscope. This is why it's all gray. And here's the transitional unit, unit 2, and the Strombolian unit, unit 3. And you see the size of the bubbles is very different. The shapes of the bubble is very different. The sizes are a bit more roundish. The vesicles are larger. We have coalesced vesicles down here. So this was all happening in a rather fluidal stage. While those bubbles here, they are far more irregular. They are strung out and they are smaller. They were not allowed to grow quite as big, meaning that there was more of a chill there. And this could be an indication that water was present here because it would actually mean that the system is cooling more rapidly, more efficiently. So smaller vesicles and less roundish vesicles. So very important observation here. So summarizing Los Erales, Unit 1 samples contain angular fragments that have been rapidly quenched and contain high levels of palagonite and also zeolite overgrowth. Unit 3 samples are regular and they then have vesicle diameters between 20 and 100 in Unit 1, but exceed 200 in Unit 3. So the tephra shapes, the particle shapes are different, and of course also the bubble sizes are different, and we even have droplets, as I said, in Unit 3 in the Strombolian one. Smaller vesicle sizes likely due to rapid quenching of the magma, increased pressure, added volatiles inhibiting vesicle growth. You can read up on the rationale behind this in Fischer and Schminke 84. So Los Erales has microscopically all the signs that we were expected, that we were hypothesizing to see, and they meaning they imply that degassing was different and the eruptive energy was different, and external water was likely playing a role in the lower part while it's not having a big role to play in the upper part, meaning that there was water initially present, but then this water got exhausted. Now, where does this water come from? That's the big question here. So Los Erales is 100 meters above sea level. And that means, well, even with sea level changes and things, it's very hard to make this a seawater phenomenon. So the cones along the lineage are lower down. They don't show phreatic features. So those that were even closer to the shore in the lineament don't show more phreatomagmatic signals. So it's not that. There's something special to be learned. There's one exception, of course, and that's Montaña Amarillo. That's the one that sits right at the coast, and that is almost entirely phreatomagmatic. So here's Amarillo, and this is Kevin and Hillary here logging the sequence here. Here we have a little bump sack, and this is very typical for phreatomagmatic eruptions here, the very finely layered palagonite ridge, and we see the entire palagonite brownish kind of tephra layers here at Amarillo. So this sinter cone was entirely phreatomagmatic due to its presence at the coast. And here's some details. The bump sacks, meaning that there was soft sediment, likely wet sediment. And here's one of these bump sacks from above. You can even get a sense for the direction, how it came in. And here the direction would likely be probably like this, with splurching the things out this way. So, and yeah, so here we have a clearly super phreatomagmatic sequence, and actually is very intriguing. Here we also have billow basalts here next to Amarillo, and we have these sand dune deposits here that are interfingering with the phreatomagmatic deposits. So this is purely phreatomagmatic due to seawater. Higher up in the sequence, we don't have phreatomagmatic phenomena, but Los Erales has some. So here we have the sequence with Amarillo at the coast, and then we have non-phreatomagmatic ones, and then higher up we have phreatomagmatic ones. This implies seawater is not the thing to look for here. We need a different type of water source. So looking at Los Erales and its exact position, we actually find that there's a little barranco here. And on the map, there's even an old spring. So it's actually in a paleo valley. And there is this spring, as I said, and there seems to be, at least in the past, there seems to have been a water source. The spring is, as far as I understand, no longer active. But there we could have had seasonal water or groundwater. And this would make sense if we had seasonal or groundwater, because that could well get exhausted with eruption duration. So my gut feeling is that the barranco may have been the answer. And here we have a little sketch. So we had some depression, a valley with seasonal water, and it just happened that the eruption started when there was water in there. It could have also been a shallow groundwater level, of course. And then the initial eruption activity was phreatomagmatic, but then the water got exhausted, and eventually we had a strombolian eruption. Now, in reality, this can, of course, mean that it could also be the other way around. It could be that an eruption starts strombolian and becomes phreatomagmatic later. If, for example, seasonal water is suddenly added, if there's rainfall, if there's flooding or things like that. So that's an issue here. We published this already in 2005 in a Spanish journal, and a few years later in an international journal. And I'll put the link to the paper in the box below. If you're interested, you should be able to download it. So a few words about this phenomenon, because it's actually a widespread phenomenon. Here we have other examples, and here we have another amarilla, because it denotes the brownish color. And that's on La Graciosa and Lanzarote. And here we have these cones that are close to the coast. They clearly have interacted with seawater. So there you need to be careful. But looking at other islands, La Isleta on Gran Canaria, for example, there we also have these cones. And also here, when we look from Fuerteventura towards Lanzarote, we have these coastal cones. And that means coastal areas affected by eruptions. Well, that can be a bit dangerous, because you might get highly explosive activity. And this is something that needs to be taken into account during hazard assessment. Then here, Caldera Blanca on Lanzarote is a somewhat wider crater, and it's got a tuff ring, and this was also affected by water, but it's not close to the coast. So obviously groundwater or maybe seasonal water plays a role. So assuming that all inland volcanoes are just merely strombolian, that is too simple, unfortunately. And we need to be prepared, because the hazard footprint, the hazard radius of a phreatomagmatic eruption could be well over a few kilometers, while that of a strombolian eruption is maybe a kilometer maximum. Not talking about lava, only about pyroclasts. So, and here El Golfo Lanzarote is very nice, very scenic. This was right at the coast. And again, we see that there's a transition from the palagonite-rich lower part to the more transitional features as fine layers here, but no, not so much palagonite, meaning that there was also a change. Maybe it got the vent got isolated from the coastal waters after some activity, and then a more transitional period or even Strombolian activity ensued. So these changes are something we need to be aware of during assessment of these eruptions. So, but there's also Mars. There's some big Mars, and here Los Marteles, and this is up there in the high mountains of Gran Canaria. So it's up here, and you see it here. So this is a big big explosive eruption, and it threw out a lot of material. And it starts off with these kind of brownish areas, and then a lot of country rock material, and eventually it goes into these more Strombolian type materials. So again, a big phreatomagmatic explosion that was grading into a more Strombolian event. And here, Caldera del Rey on Tenerife. There we have a big sequence, and Juan Carlos and I, we did a video on this recently, of a big sequence of phonolithic tephra that was also affected by water. And there we have these impact sacs, telling us there was soft, wet substrate, and that implies there was a lot of water involved, high fragmentation, big fragments being thrown around. So this was quite an explosive eruptive sequence at El Rey. And here it's actually quarried right now. So, and it's used to make cement and things like that. So very intriguing sequence of eruptions. It's a Mar-type volcano as well, with a tuff cone surrounding it in southern Tenerife. But again, this is prehistorical. So, but I want to just make a few points about historical phreatomagmatic eruptions. And this is going back to prior to the 2021 eruption. But there was an eruption in 1949 on La Palma, which was described by Andreas Klügel in 1999. And the 1949 eruption started here on the crest and here. And one lava was going downhill towards the west. The other one was going downhill towards the east. So two main vent systems that were active. And up here we have Hoyo Negro and Duraznero. And here we have another vent. And this is a photo from 1949, a big phreatomagmatic explosion, actually. This is the Cumbre Vieja Ridge, and the 1949 eruptions are up here, right on the highest part of the ridge. So this has nothing to do with seawater, and there's not a lot of rainwater up there either. If it rains, of course, it can lead to some explosions, but this is not raining here. So water was either groundwater or in some other form, it was added to the vents. We recently found some sedimentary nodules around some of the vents of the 1949 eruption. Another speculation is that water could be released from sediment that was picked up. So in any case, phreatomagmatic eruptions are possible. And here is the Hoyo Negro crater. I think it should be Negro, not Negra. And these images are courtesy of Andreas Klügel. So here we have these finely laminated, very finely fragmented, high energy material. Fine fragmentation means high energy of the eruption. And we have these impact bomb sacs here as well. And that again means very soft substrate, very wet, soft substrate. So here's a few images of this sequence. Here again, the eruption from 1949, and this is very explosive. So this is not rain, and this is not seawater. So other sources of water, like groundwater, or potentially water added from country rock material that was assimilated, could be the answer. The important thing is that not all volcanoes will behave the same, even if you're inland and far away from the ocean. So this is very important. And if we look at some historical drawings like this one here from 1677, it looks rather energetic as well. So maybe there was phreatomagmatic episodes during the eruption 1677 as well. So this phenomenon is widespread, and in many of the hazard assessment, hazard maps, most of the vent alignments are marked as likely bringing up Strombolian eruptive types. And here we need to be a little careful. Fissure-fed eruptions are common in the Canaries, and they can not just form Strombolian eruptions, they could also have phreatomagmatic explosivity. And this is not just at the coastline, this is also inland. The exact reasons may differ. It could be seasonal surface water, there could be groundwater, there could be even water from country rocks that is added, but we see the phenomenon to be widespread. So we need to be aware that eruptions inland can also have phreatomagmatic activity, and we need to take that into account. And this can change during an eruption. It might start as explosive eruption and then go strombolian, or it could be strombolian and then go explosive if groundwater breaks through, breaks into the vent, or if suddenly surface water is added during rainfall, maybe a flash flood would affect the volcanic system. So these phenomena will potentially make seemingly harmless eruptions dangerous, or could, of course, in the other way, make rather explosive eruptions less dangerous. So the changes are important here. That's the point I want to make. We need to be aware these are very dynamic systems, and we cannot just assume one eruption time for these alignments. So eruption styles along fissure systems may be highly variable, and we cannot just assume that they are strombolian by their very nature. So thank you very much. And you can also kind of give some credit here to Juan Carlos and to Hillary. And I say thank you very much for your time. I hope that was useful. And please download the paper if you're interested. And I say all the very best. Thank you for your interest. And I'll talk to you again very, very soon. Bye-bye.